So Dennis Conti is the chair of the AAVSO Exoplanet section, and he is a whiz at observing these exoplanets, and I am very excited to hear about this because I know this is an activity that I want to do myself. So without further ado, I'd like to have Dennis present.
Okay, thank you, Joe. Let me share my screen here.
That's okay. I'm not going to be.
With me. Let me. Can everybody see my screen? Okay, Joe.
Yes.
Okay, great. Okay. Well, thank you all for inviting me. Very pleased to have the opportunity to hopefully share my excitement about exoplanets, in particular, how we amateur astronomers can not only observe them, but as you'll see, actually contribute to exoplanet science. What you see on the main screen here is an interesting exoplanet. This, of course, is an artist's rendition of an exoplanet that is orbiting a close-in star, which is in the upper right, the upper left. And both that star and the exoplanet are themselves orbiting two other stars. So it's a triple star system. So if you were to be able to stand on this exoplanet, you would actually see three stars, your host star and two other stars that you and your host star are orbiting. This is one of the crazy exoplanet configurations that we are now discovering, and some are even more bizarre than what you see here. So what I will be covering is, as the title sort of implies, is the wacky world of exoplanets, namely all the different types and variations of exoplanets, but also how we, and by we I mean literally we amateur astronomers, help the professionals to discover them. And hopefully, if any of you become interested in this, I'll show you a way how you can contribute to exoplanet science. So let me start with the big picture. And if we kind of step back and say, what really is NASA's goal in all of its planetary science missions? Well, the basic question I think we would all agree that we as humans are trying to answer is, are there planets outside our solar system, maybe exoplanets, that support some kind of life? And by life, I don't mean, ET running around, but even some type of microbial life. But scientists believe that in order for a planet, an exoplanet, to support life, it really should be rocky. So the questions that we're asking in our exoplanet science missions are we finding planets that in fact we think are so-called terrestrial, that is to say rocky? Do we think the planet can support liquid water, which we believe is an important part of sustaining life, at least as we know it? Do we think the planet has an atmosphere? And if so, does the atmosphere contain biosignatures that give us a hint that there is some kind of life that exists on the planet? Now, one of the things that exoplanet scientists are realizing is that whereas we thought that certain biosignatures like, oxygen, methane, that sort of thing, would be signatures of life, many are now finding that, unfortunately, some of those biosignatures might be caused by geophysical events on the planet itself, as opposed to coming from some kind of biological origin. So that's now kind of complicating a little bit whether we can find true proof of life on some of these exoplanets. But I think probably in the not too distant future, I think exoplanet scientists will come to a resolution on what do make up biosignatures that give high confidence that life does exist. So these are probably some of the most important questions that exoplanet scientists are trying to answer. And for these reasons, these questions, in fact, really define NASA's mission. I'll kind of jump ahead and tell you that we're really now well into question number 4, if not 5. That is to say, with James Webb Space Telescope, for example, we're really now starting to answer all the way down to question 4. Well, I think surprising to many people is that we're now finding that most stars, probably close to 90%, have one or more planets orbiting them. So if you look up at the night sky and you see twinkling stars, probably there's a good chance there's planets orbiting those stars, if not one, but maybe more than one planet. Some of the planets that are orbiting these stars, from our point of view, pass directly in front of their host star. And we call those transiting exoplanets for obvious reasons. Some might be orbiting the star in a circular fashion where the planet is not passing in front. But even with those types of exoplanets, we're still able to detect their existence. And I'll describe some techniques later how that can happen. You'll see in a minute that exoplanets come in all sizes, from Earth-sized planets to planets many times the size of Jupiter. The smaller the planet, obviously, is more difficult for us to detect. The larger the planet, close to the size of Jupiter, actually fairly easy. In fact, with our backyard telescopes, we're able to detect transits on the order of Jupiter-sized planets. So if we look at the different types of exoplanets and the different orbital orientations, one of the type of exoplanets that has been the most discovered, mostly because of observational bias, because they're easier, have been so-called hot Jupiters. These are close-in planets to their host star, therefore hot because they are hot, close to their host star, and they're large, so therefore Jupiter size or greater, and so therefore they've been called hot Jupiters. They will orbit their stars on the order of a few days, maybe even in some cases 1 day or less. So very close to their host star, very large, and therefore very hot. We have detected that there are some stars that have multiple planets in them. One of the most famous that has been discovered rather recently, actually, is the TRAPPIST-1 system, where about 4 or 5 of these planets orbiting the star are within the so-called habitable zone. So in fact, the TRAPPIST system is a prime candidate for the Webb Space Telescope to try to characterize their atmospheres. Some planets orbit in a multi-star system, as we saw on the opening slide. And some planets actually are free-floating. For various reasons, they've escaped and been forced out of their system around their host star and literally are floating free in our Milky Way galaxy. Interestingly, we have some planets that orbit in the opposite direction from the rotation of their host star, which is sort of counterintuitive because, as we'll see a little bit later, planets form out of the circumstellar disk that itself formed the host star, and therefore you would think that the same angular momentum would apply to the planet. Well, these planets that are orbiting opposite from their star's rotation, one possibility is that they were captured by the host star, and therefore their orientation, their orbital orientation, is different from the original spin orientation of the host star. And finally, we've detected planets that are disintegrating around their host star. A very famous one that I use throughout here as an example is something called WASP-12, which was discovered a few years ago, but exoplanet scientists are now seeing that its orbit is decaying, and sooner or later it's going to be disintegrating. We've actually observed, and I even with my backyard telescope have observed these segmented clumps of planet that represent most likely a disintegrating exoplanet. So how are exoplanets formed? Before we answer that question, it's important to understand how the stars that they orbit are formed. If you saw the initial set of images that came from the Webb Space Telescope, this was one of the ones that was released that is one of the most amazing ones. This is a star forming region of gas and dust that are the birthplace for stars. And that leads to how stars are formed, which we'll show in a minute, lead into how planets are formed. So the first thing is this cloud of gas and dust. Clumps form from that cloud through just gravitational wells that form in that cloud. The clumps get denser and denser, just again through the accretion of the gas and dust material into tighter clumps. And finally, the cores condense and young stars are formed from these within a dusty disk. The best way I can explain how this happens, imagine an ice skater, where the ice skater pulls his or her arms in, and therefore the rotation gets faster and faster. Because of the conservation of angular momentum, the same applies here with the star, that as a star gets more and more dense inside, it spins faster and faster. But the other analogy, however, would be like a pizza dough that you would throw up in the air. If you throw up in the pizza dough in the air, it starts flattening out. And the same here would happen here with this disk of gas and dust, that as it's circulating around a star, it starts spreading out. And when it spreads out, just like the way that the star initially formed, clumps of material start aggregating together, and that's how planets are formed in this disk that has been formed. In fact, what you see here is in fact a image taken with a space telescope, actually a ground-based telescope. And what you see are these little indentations in the ring that we believe are planets being formed that are clearing their path around their host star. So literally what we're seeing here is the birth of a planet around its host star. So to understand how stars are formed, it's important to see how planets are formed. Now, one of the things that exoplanet scientists still are trying to grapple with is, how is it that we have some planets that are formed quite a bit away from their host star, and some very large that are formed quite close. They're not sure if the ones that are very close have migrated in from the external part of the disk, or if they in fact were formed in situ. So this sort of summarizes sort of what we just said, that material from the star's disk clumped together, the core of the planet starts forming. As I said, some planets form close in, some form at a distance. And depending upon where the planet forms, just like in our solar system, if it's pretty far out, it might be a gas giant. If it's further out, it might be an ice giant. Or if in fact is neither one of those two, if it's formed at the right location with the right density, it might be a rocky planet like Earth. So our solar system has some analogies to the different kind, in fact, of exoplanets that we have discovered. And in fact, a planet itself may have its own disk of material that would clump together and from which moons around the exoplanet itself may form. So how are exoplanets discovered? There's a couple of major methods by which they are. One is the transit method, the other is radio velocity. With the transit method, as I said earlier, if we can observe a planet passing in front of its host star from our line of sight, then what we'll see is a dip in light of the star's light as the planet passes in front of it. And this dip in light, as we'll see in a second, gives us a lot of information about the size of the planet. It doesn't tell us anything about the mass of the planet, as to say, you know, how much it weighs, but it does tell us enough about this radius or size of the planet. The radio velocity method, however, provides that other crucial piece of information, which is the mass of the planet. And it does that by using the fact that as the planet is orbiting the star will move back and forth from our point of view. And just like a Doppler effect of a train, you know, going toward us and then away from us, the frequency of the spectrum from the star's light will change. And from that, we can deduce the velocity of the star's movement. And from that, the mass of the planet that has caused those Doppler effects. So with the transit method, we get the size of the planet. And with the radio velocity method, we get the mass of the planet. And combining those two, we can therefore get the bulk density of the planet. And of course, the bulk density helps us answer one of those prior questions, which is how rocky is the planet? And again, those two methods are complementary to each other to help us answer the question as to the composition of the planet. There's a couple other methods that also are used, one called microlensing, which is basically gravitational lensing, if you've heard of it, where a body in front of another light source can cause the bending of light, and then based on the characteristic bending of that light, scientists can determine if, in fact, there's a planet orbiting a star in that foreground star system. Astrometry, which is another method which measures small changes in the movement of a star. So the transit method, however, and the radio velocity method are the most popular, and these have helped inform us as to the composition of exoplanets. Now, what I'd like to focus on really through the rest of this presentation is the transit method, since this is the dominant method that we amateur astronomers as well as professionals use to detect exoplanet information. So what you see here in this little graphic is in fact a planet going around its host star, and as it does it, if we were to take a look at the light of that host star or the flux of the star, what you would see is this characteristic bucket-shaped curve, where as the planet goes in front of the star, some of the star's light is obstructed, so therefore the amount of light from the star takes a dip and then it goes back up again. And that particular curve is very crucial to helping us understand a number of things. So in fact, we can get a lot of information from just the light curve, from the duration of the light curve, the depth of the light curve, the shape of the light curve. For example, the depth of the light curve helps inform us as to the size of the planet, because as you can imagine, if the planet were larger, then a larger portion of light from the host star would be obscured. The shape of the light curve helps us to determine whether in fact what we're seeing is a planet going around a star, or in fact maybe it's two stars that are eclipsing each other, which would have a different characteristic shape. So just the shape alone of the light curve will help us determine if what we're seeing is a planet orbiting a star or two stars eclipsing each other. So the information then that we do get is the size of the planet, as I said, from the depth. We can get the size of the orbit, and we can get the inclination. So these are all three critical pieces of information about the exoplanet that we can get simply from the light curve. So the light curve becomes very important observational set of data that we collect here on Earth, but also from space telescopes. And I'll talk about that in a minute. In fact, let's talk about it now. So the one of the current exoplanet discovery mission that NASA currently is conducting is with a space telescope called TESS, Transiting Exoplanet Survey Satellite. And as the name implies, its focus really is on transiting exoplanets, where again, the planet passes in front of its host star. And it's a survey satellite because literally it is looking at the entire sky, except for little pieces here and there around the ecliptic. TESS consists of 4 cameras that dwell on a certain sector for up to 27 days, and then it moves to the next sector. We're already well into a multi-year TESS mission. TESS was launched in April 2018. So we're now into the 5th year of TESS. It's already gone through a primary mission and it's into its 2nd extended mission. The focus of TESS is on bright nearby stars. And by nearby, we mean within 30 to 300 light years. The TESS mission is distinguished from, you may have heard of Kepler. Kepler mission focused on a small patch of sky as opposed to doing a survey. And it focused on sun-like stars that were further away than the stars that TESS is looking at. In fact, one of the primary missions of TESS is to help find candidates for the James Webb Telescope to characterize their atmospheres, which in fact it has done. It has already met and exceeded its mission requirements. To date, literally as of today, TESS has found over 6,000 planet candidates and has confirmed 285 exoplanets. And this is a key distinction I just want to mention between candidates and confirmed. Candidates means that the TESS satellite has seen a dip in light of enough magnitude to rule it as a possible exoplanet. But as we'll see, a dip in light could be caused by a number of different things. It could be caused by exoplanets, but it could also be caused by other false positives, as we say. So even though there's 285 confirmed exoplanets, there's still a lot of candidates that still have to be vetted. And there's a very, very rigorous routine that the professional astronomers go through to go from planet candidate to confirmed. And it's this vetting process where we amateurs play a huge role in helping the professionals make that transition to confirmation. And we'll be talking about that in a minute. So what you see here is the total process for going from a candidate that TESS is identified all the way down through to final confirmation. And it involves a number of different scientific observations that have to be done. The very first is that from ground, we being amateur astronomers, along with professionals, do observations of the star system that TESS believes is a exoplanet. So we start with an exoplanet candidate. We do ground-based observing to try to rule out any false positives. Once it passes through that gate, then there is higher resolution imaging that's done to rule out any nearby contaminating stars. There's spectroscopy that's done to get a better handle on the characteristics of the star itself. And then we do radio velocity studies where the mass of the planet is determined. So starting from the top, if we pass through the first gate, we get an idea of the radius of the planet. And if we pass through the bottom gate, we get an idea of the mass, and out pops an estimate of the bulk density of the exoplanet. So this is the pipeline that scientists, TESS scientists go through, and where we amateur astronomers play a big role is in the first box, the ground-based follow-up, because this is where we weed out any false positives and can help confirm that in fact it's a true exoplanet transit. So why do we need to do ground-based observing if we have this fantastic telescope in the sky? Well, because it's a survey satellite, multiple stars get blended together in a TESS image. And we'll see in a minute the fact that the TESS pixel is almost 20 times larger than our ground-based CCD cameras that we amateur astronomers use. It's easy to blend together multiple stars. So a dip in light that TESS sees could be caused by a true exoplanet transit, or it could be caused by a number of different false positives. And for this reason, we need to follow up on the ground to sort out what are true, really exoplanet transits versus those that are false positives. Now, to show this a little bit better, this is an image I took from my backyard telescope of, if you sort of keep your eye on the two stars in the middle, and if we zoom in on those two stars, what you see here is on my CCD camera, you see the pixels that make up that part of the image. And you see that a star itself consists of maybe, I don't know, 10, 12 pixels across. Well, what we're able to do on the ground, because we have these small pixels, is to be able to separate out these two stars, the light from the two stars. And we're able to measure any changes in light from the two stars. However, TESS's pixel is, as I said earlier, about 20 times larger. So if that's our ground-based pixel, this is TESS's pixel. And so in a single TESS pixel, the two stars that we see here would be blended together in one blob of light. So TESS itself would be able to see that there's a change in light in that pixel, but it's not able to really finally determine which star caused that change in light. So therefore, we on the ground would reobserve that star system and distinguish then which star was causing the drop in light. So that's why ground-based observing is needed. And it simply is the fact that for TESS to do a all-sky survey, it has to have these large pixels. Now, here are some scenarios that sort of would confound TESS. What we see here is a case of a star on the left, and next to it, an eclipsing binary. That is to say, two stars that are orbiting each other. We call this a nearby eclipsing binary simply by the fact that it's an eclipsing binary nearby the target star. From TESS's point of view, all of these three stars might be blended together. So when the eclipsing binary is occurring, TESS is going to see in the blob of light of all three stars, is going to see a drop in light, but it will not have been able to distinguish where that drop in light is coming from. We on Earth, because we're able to separate out the star on the left from the eclipsing binary on the right, would be able to say, nope, this isn't happening on the target star. It's an eclipsing binary next to it. So check it off as a false positive. This is one of the more common cases of a false positive where we amateur astronomers are able to help the TESS team determine whether in fact it's a true exoplanet transit. The other case where it would be if this nearby eclipsing binary is so close to its host star that even on Earth from our backyard telescopes, we're not able to make that distinction. This would be a case where we would have to pass it off to a larger professional observatory to help separate out the two systems. Another case is where a star is orbiting a nearby eclipsing binary called a hierarchical triple, where in fact the blending of light would have the same effect as earlier, where TESS would think there's a transit of a planet taking place, when in fact it's really just a transit of two stars orbiting each other. This next case is where the target itself is an eclipsing binary. And again, TESS is not able to distinguish it, but we on Earth doing our observations are able to make that distinction. As is the case here, where there's not even something near the star system, but the secondary star is small enough that in its orbital alignment, it does appear to be a planet. And in fact, we'll see how we're able to distinguish this from it being truly a planet versus an eclipsing binary. And finally, we have the case where two stars are such that one is grazing the other, and it kind of gives a false notion that there's a planet that's actually transiting it, because there's just a small dip in light from the host star. So all of these cases, or most of these cases, are ones that we on Earth are able to distinguish. And we do that in a number of ways. One is just by looking at the shape of the curve. If it's this bucket-shaped curve, then most likely it's an exoplanet. If it's V-shaped, more than likely it's an eclipsing binary that is causing the dip in light. If it's a V-shaped curve and it's alternating in depth, then definitely it's a eclipsing binary as opposed to a exoplanet transit. If we take a look at the star system in different filters, let's say a blue and a red filter, and we see that there's a variation in the depth of these transits, that's another clue that it's not an exoplanet that's transiting, but it's two stars orbiting each other. Because if it were a planet, there would be no change in the depth based on color, as opposed to if it was two stars orbiting each other. So based on the shape of the curve, the alternating odd even V-shaped of the curve, whether the depths are changing with different filters, we're able to determine if it's a exoplanet transit or not. And finally, just simply looking at the size of the depth, if it's greater than 2.5 Jupiter radii, then more likely it's not a planet, it's a brown dwarf, or it's a star orbiting another. So again, just based on the light curve, we can get a lot of information. So what I wanted to show here is an example of detection of a nearby eclipsing binary. This, in fact, was a colleague of mine, another amateur astronomer up in upstate New York. We're trying to determine whether a particular system was an eclipsing binary or whether it was a exoplanet transit. So he took this light curve in with a in a V-band filter, and as you see, the depth is what you see there. I took the light curve, did the light curve again, and with the same filter, but what you see if I put them on top of each other, that they're alternating in depth. And this sort of nailed the fact that this is an eclipsing binary versus a exoplanet transit. So we wrote that off as a false positive. So these are the sorts of light curves that we amateur astronomers can do from our backyard telescopes that help the professionals in discerning whether a TESS candidate is truly a exoplanet or whether it's something else, such as an eclipsing binary. Now things get a little complicated because of this blending of light from TESS, that even out to 2.5 arc minutes from a target system, TESS can blend stuff together enough to confound whether or not what it's seeing is an exoplanet. And in fact, here's literally close to over 100 targets that potentially could be culprits in confounding TESS. And it was the case that each of these targets had to be individually tested from the ground with different analysis techniques. But we amateur astronomers actually were able to figure out to help the professionals able to do this analysis much more quickly. And our contribution was not only from the standpoint of being able to do observations, but actually to help with software to help streamline the process. So what equipment is needed to observe an exoplanet? Well, in my own case, I have an 11-inch telescope. That's probably on the lower end of doing what I'll call exoplanet science. Although some folks have used 4.5-inch telescopes that can be used to detect large hot Jupiters. And in fact, some of those are contributing to determining whether in fact the midpoint of the transit is varying from observation to observation. A reasonably good mount. It doesn't have to be top of the line. I have a Losmandy G11 mount. It's got reasonably good tracking. It does require a guide camera to stay within a few pixels throughout a 4 to 6 hour observation, but it does a fine job. And I've been using it for literally 10 years now, almost. A modest CCD camera or CMOS camera is fine. A guide camera, guiding is I would say necessary to do exoplanet observing, and ideally at least one filter, such as a V filter. So those of you who are doing deep sky imaging already can see that probably you got most of the equipment already here to do exoplanet observing. In fact, that's where I came from. As I said maybe earlier, I came from deep sky imaging and planetary imaging, getting into exoplanet observing with very little changes in equipment. There is free software available to do the reduction and analysis, so that's not necessary. Of course, the other software, just as with the deep sky imaging, such as camera capture software, and planetary software such as SkyX or Maxim DL would be certainly necessary. Now, what type of local conditions are needed? Well, I'm here in suburban Annapolis, Maryland, and already in moderately light polluted skies, and I'm able to do science grade exoplanet observing. Obviously, I would be able to observe if there's a clear sky, even though if there's some high thin clouds, that's fine. And, moderate to good seeing conditions. Here I can get, maybe 4 arc seconds, hardly better than that, but that's fine. And as an example, this light curve that I showed earlier, in fact, was done from my backyard telescope here in Annapolis. So just to kind of summarize in terms of equipment that are needed and in terms of local conditions, pretty close to probably what you might be doing with your deep sky imaging right now. So to summarize, I think hopefully you've seen that amateur astronomers have contributed greatly to exoplanet discoveries. The majority, in fact, of the TESS follow-up observations are being done by amateur astronomers. As I said earlier, we help develop not only the software, but also we develop the guidelines for how folks should submit their observations. We developed the process for clearing out a field of false positives. And some of us even have access to large remote professional observatories and are given access to 1 meter telescopes to the images that are collected from there, so we can do the analysis of those observations. So where's NASA going from where we are today? Well, obviously, the James Webb Space Telescope is huge in terms of the next steps in answering those first set of questions that we identified at the beginning of the presentation. As you may know, the Webb telescope observes in the near infrared, and its purpose, one of its purposes, is to characterize the atmosphere of exoplanets, which helps us to get down to the bottom of those questions to help answer whether or not there's life on some of these exoplanets. The next space telescope to be launched in the late 2020s is the Roman Space Telescope. And for the first time, to a large extent, we'll be able to do direct imaging of exoplanet atmospheres. Now, by direct imaging, we don't mean we're going to be able to see, mountains and oceans, but rather we'll be able to more directly see the light coming through the atmospheres of exoplanets, and to be able to help distinguish the elements that might be in the atmospheres, which gives us a better handle on, again, some of the potential biosignatures that might be there. So to summarize, I think hopefully you've seen that we've contributed greatly as amateurs to confirmation and discovery of exoplanets. It takes not much more than astroimaging experience to get involved in doing exoplanet observing. And the TESS mission in particular gives a great opportunity for contributing to real exoplanet discovery and science. And in doing so, many of us have been named as co-authors on discovery papers. I myself currently are on, I think it's up to 27 refereed published exoplanet discovery papers. So it's kind of thrilled to be part of real science, as you're seeing here. Now, the AAVSO, which I'll talk about in a second here, does provide everything you need to know as far as doing exoplanet observing, from the training to the software to mentors to forums. So just a few words about the AAVSO. Goes back to 1911. AAVSO stands for American Association of Variable Star Observers, but it really is broader than variable stars. It's an international organization, primarily of amateurs, to advance the science of astronomy. We do that through professional amateur collaborations. We archive our observations on long-term databases, and we have refereed publications in the Journal of the AAVSO. As I said, we have all the tools and training needed for our members to conduct science-grade observations. We have an annual meeting where we interact with each other. Presentations are made, workshops are done to help advance each of us in our knowledge of particular areas. The core to the AAVSO are its sections. Each of the sections provide training and courses and so on different topics. And these sections range from everything from supernovae to eclipsing binaries, high energy networks, spectroscopy, solar observing, and of course, my favorite, exoplanets. And in the exoplanet section, we have observing courses. Now, I want to highlight the fact that, in fact, beginning February 6th, I will be conducting an online exoplanet observing course. And if you're interested, if you go to the AAVSO main website and navigate to the courses, if you sign up for a course, it will be over 6 weeks. It will be conducted on Mondays, beginning at 7:30 Eastern time. And it'll basically walk you through just about everything you need to know to get started on exoplanet observing. Short of that, there's a guide on my website called A Practical Guide to Exoplanet Observing, which talks about the best practices of exoplanet observing, leads you through the software that's used to do an analysis. And from my website, you can actually get a set of test data that you can use and follow in the guide itself, uses that same test data. We have a qualification program for AAVSO members who want to participate on the TESS science team. Currently, we have 26 members qualified who are helping right now with the TESS professionals do exoplanet science. And finally, we wanted to make an offer to you as a club member who kind enough to listen to this presentation, that if you're interested in joining the AAVSO, we are offering a reduced membership rate of $40 for the first year, which is a great bargain because it gives you all kinds of advantages in terms of reduction of rates of the courses, reduction of rates at our annual meeting, access to different forums, access to different tools, and so on. So it's a pretty good deal. And if you are interested, if you just shoot an email to avso@avso.org with subject line club membership, include your name and the name of, in your case, New Hampshire Astronomy, Astronomical Club, then you'll be given information how to sign up. And if you need further information, feel free to contact me and at dennis@astrodennis.com, or go to my website, astrodennis.com. So with that, Joe, I think we have some time for questions. If you want to open it up and moderate any questions, or if anyone wants to join in or raise their hand or whatever.
Very good. First of all, Dennis, thank you very much. Captivating presentation, and I'm really, really interested in this. I guess I'll start with the first question. Why a V filter?
Well, a couple of reasons. One is it's a standard photometric filter. And so it covers a broad range of bandwidth, obviously. Now that would be what I would call sort of routine exoplanet observing. It is the case, however, if you were to, in fact, be part of the TESS science team, that you will frequently be asked to observe in a particular filter, typically a blue filter or a red filter, in order to help distinguish that different chromaticity depth I showed earlier. But I say a V filter simply because that's, just a standard run-of-the-mill photometric filter that covers a broad range of bandwidth. But for I would say more science grade observation, then probably one of the other photometric filters would be useful.
Okay, thank you. Any other questions? Feel free to unmute yourself and ask Dennis. We unmute people.
Well, I'd like to say thank you first, Dennis. I just do visual observing, but I found your presentation very enlightening, and I didn't realize that we could be that involved with science as we could be.
Right. Yeah. I think honestly, I think many amateurs aren't aware of, in fact, not only with exoplanet observing, but at the AAVSO in even the other areas in terms of really being involved in contributing to science. I know for myself, that's kind of what turned me on to exoplanet observing, the fact that I was literally contributing to astronomy science.
Any other questions? Feel free to either raise your hand or unmute yourself. Cheryl?
Yeah, that was a really nice presentation. Thank you. I was curious how you had those curves, the V curves and then the U,
Right.
and depending on the depth of it, you could tell whether it was a star or, you know, larger than a Jupiter-sized planet.
Right.
Those seem like really, really precise measurements with the, you know, something like a backyard telescope. How do you just take a lot of measurements in order to make sure that you can get the error down? Because it seems, you know, you're talking about a pixel here and a pixel there. And do you observe over like a long period of time all around for years before you do this? Or how do you get the error down?
Okay, very good question. Let me back up to one of these light curves and kind of go from there. So let me just go to main light curve here a minute. So let's take a look at this light curve. So each one of those dots, this for example, from left to right is about a 6-hour observation. Each of those gray dots is 45-second image of a star field. And so each exposure is 45 seconds long across over, like I said, maybe 5 or 6 hours. And each image, let me just get an image of a star field here. Let's say this is a 45-second image. And let's suppose that this center one is the target that we're trying to determine if there's any change in light. What we do is something called differential photometry, where, and there's software to do this, so it's actually quite straightforward. What we do is we put literally a aperture, not a telescope aperture, but a photometric aperture around that star and other stars that are close to it in magnitude. And what we do is we just record the ADU counts of that star, that target star, relative to the ADU counts of stars that are presumed to be non-varying. And as the name implies, differential photometry, if we see, let's just say all things being equal, as the seeing changes, the target star and the comparison, the other stars are going to go up and down in the same relative amount. If there's a planet going around the target star, it's going to drop relative to the others more. And that relative difference tells us that, in fact, there is a transiting body on that center star. So we do that over, as I said, over 4 to 6 hours. And each of those gray dots here represent the depth change of that star. Now you see here that there's some scatter just simply because of changing seeing conditions. The green represents 5-minute averaging. And as you see, to take out any variability, if you just sort of follow the green dots, and what the software does is it applies a best fit model. That's how we get that curve. So it's based on individual observations using differential photometry to give us the relative change of the target star. And that's how we get the curve. Does that help?
Oh, yeah, and it also explains, I was curious about how you avoid seeing effects, or how you,
Yeah, right.
hostage to the seeing, but yeah,
Right.
thanks. That makes sense.
Yep. Yeah. If all the stars have the same effect, not only in terms of different seeing conditions, but as you may be aware, as the star is rising, let's say, in altitude, it's going to have different atmospheric extinction. And in order to compensate for that, the presumption is that all the other comparison stars are having the same effect as the target star. There are some cases where I won't go into, where we have to compensate for different colors of different stars, but nevertheless, that's how it works. It's all relative to presumably non-varying stars, and these represent the difference from those non-varying stars.
Cool. Dennis, are eclipsing binaries and stars, and with all the reference stars in the field, I assume it's a pretty low chance that one of those would be an eclipsing binary and confound the measurements, right?
Yes, yeah. The eclipsing binaries are the biggest culprit in with respect to TESS, at least, thinking that there is a true transit, and that's why we have to look within a certain radius to determine that, in fact, we would have to look at a certain radius to make sure that these stars around our target are not eclipsing binaries, because that could confound TESS.
I see.
And how do you determine if the stars are nearby or variable themselves? Do you have to account for that?
Yes, so the software itself can plot the light curves of the comparison stars, and if we see any that themselves are varying, then we just click a button and it eliminates it from the measurement. So it's very easy to determine and to get rid of any eclipsing binaries that might be confounding our analysis.
Or you could be discovering a planet somewhere else, right?
Well, in fact, we have one colleague of mine, in fact, discovered his own planet, not through this means, but on his own little discovery mission he put together.
Is it really possible to do that? It's got to be some shots in the dark.
It is, and he did it. His planet is called EXO-1, and yeah, it was yeah, he was able to do that.
Any other questions for Dennis? I'll take one more question. No. Dennis, we're about at the time.
Okay,
Thank you very much.
sure, my pleasure.
And I'm looking forward to doing more research and finding out more about this.
Well, great. And I encourage any of you who are interested in joining the AAVSO. We have this great deal, and if you can, take advantage of it. I think you'll find it exciting, at least as I did, as far as being able to contribute to science. So thank you.
Very good. Thank you, Dennis.
Sure. Thank you.
Thank you very much.
Thank you.
I will take the screen and share it. And I am going to, actually I have to share. I am going to stop this recording. Whoops. I don't think this worked.